Hi, this is Mark from Skywagon University doing another video about an interesting machine that flies. And the other day we did one on the Champ, and this was in the background, and several people were like, what is that helicopter? Do that K-Max. Well, then I met Kevin, the pilot, here at Placerville, because he's here on fire watch, putting out local fires, and he very kindly offered to give us a bit of a tour around it. So Kevin, thanks.
Yeah, good to chat with you, Mark.
So give us a little bit of the history of it, because it's obviously a bit of a different machine, unconventional.
It's a very unique machine. So Charlie Command started building helicopters back in the 40s and the 50s. He started taking apart tractors and farm equipment and mounted it to a flat deck trailer and came up with the intermeshing rotor system and was flying, basically scabby farm equipment around and testing rotorcraft.
Anyone would think it was an airport.
Yeah. The first aircraft that he built that was, flyable, that got pushed off to the military was the Husky. So the H-600, the Husky was used as a crash rescue helicopter. The idea was it would land right behind a jet that had crashed on the runway. The firefighters would get out the back. The helicopter produces very low rotor wash, so the Husky would pick up and hover over the crashed jet. It would blow the smoke away, and then the firefighters could go in, get the jet pilot, and pull him out. So that's kind of how they started. And then since then, Command's built a number of other airframes. The K-Max came from the Husky.
Was it always the intent to have no tail rotor?
Yes. Yep, he was always into the intermeshing rotor system. That was his kind of bread and butter.
Oh, okay.
So he designed this system. When he designed the flap system that you see on the aircraft, there were no hydraulics back then. There were no fancy rotor systems. So everything was very heavy. These blades, even today, are still handmade out of wood.
They're wood, I read that.
So at the time, he couldn't develop a control system that was soft enough for a pilot to make inputs, since there was no hydraulics. So he designed this flap system where when the pilot makes inputs, all we do is move that little flap, and then the blade bends and twists behind it. So that was kind of his unique design in that system, because there just wasn't the technology around then.
The question everyone's going to be thinking is, why don't they hit?
Yeah.
Because they're like this.
It's all luck.
Yeah.
So there's a huge transmission right below the masts, and the drive shaft comes out of the engine. It goes into a huge overbuilt gearbox, and that gearbox locks the blades exactly 90 degrees opposite one another. So those big spiral bevel gears, unless that transmission were to fail, those gears are locked in place, and that keeps the blades exactly 90 degrees off.
It's one engine?
One engine. Yep, one engine, one drive shaft, and then it's split into two that go up to the rotors.
Okay. And then the lack of a tail rotor, you were telling me earlier, is an enormous saving of power, right?
Yeah, you get, a typical tail rotor takes 30% of your power to run, and the only purpose of the tail rotor is to counteract the torque.
Right.
So by having two rotor systems that counter-rotate, that zeroes out all the torque effect where the helicopter would want to spin, and you get 30% of that power right back into lift.
So without getting to, I've only got a few hours in helicopters, what do the pedals do in a K-Max?
All the controls in a K-Max are just like any conventional helicopter. Cyclic is your directional control, collectives up and down. The pedals control your yaw. So the way they work in this system, if we push right pedal, we increase the torque and lift in the left rotor, and the counter torque, or the spin, makes you want to go to the right. So you increase the torque in the left rotor, and since we don't have a tail rotor, the helicopter wants to spin right in the opposite direction of that spinning rotor on the left.
So how does one increase torque if they link together?
Command developed a very unique mixing box right below here that we can't see, but that takes all of that input that you make, goes into the mixing box, and then through a series of control tubes, it goes up into the rotor system, and it only increases the lift or the torque in that left rotor.
Oh my God, that's amazing.
And then that makes a unique problem. So now you want to yaw, if you're in a hover and you want to yaw to the right, you push right pedal, you would just increase the lift in the left rotor, so the helicopter wants to roll over.
Awkward.
Yep, very awkward. So when you first learn to fly an intermesher, that's one of the main things you're learning, is some of those weird characteristics. You go to push pedal and the helicopter's wanting to roll over on you, and you got to counteract that with
So you couldn't just get out of a Huey, 1,000 hours in Hueys, get out of a Huey and get into this?
You absolutely could.
Oh, you could?
You could, but there's just unique characteristics that these have. So typically...
It would just be a bit
Yeah, it'd be a bit awkward.
at first.
Everyone, industry standard, if you want to transition into the K-Max, would be you go to the factory, you get in a Husky and fly the Husky, which is 2 pilots, and they teach you the characteristics of the intermesher, the fact that it wants to roll over, the dwell zone. There's a unique period in the collective where you really don't have too much control or very limited control. So the helicopter wants to kind of do its own thing. So you get used to those characteristics, and then they put you in their K-Max and you go fly.
Oh, okay.
But the average pilot, if you got in there, yeah, you'd probably get off the ground and land. It'd just be a bit awkward.
Is it like, if you said, right, I want to fly K-Maxes and you're a Huey pilot, is it like 5 hours, check out?
They actually do quite a bit of flight time. It's changed a little bit because the Husky that they have is running out of hours. But it's about 15 hours of flight time at the school that you do. And then another probably 7 in the K-Max.
Excellent.
Yep.
So here's the bucket, which always looks very small hanging underneath the helicopter. Kevin, tell us the weight it carries and how it works.
Yep. So this is a bucket made by SCI, Canadian company. This model is the Bambi 5566. It holds 660 gallons of water.
So that in weight, that's
about, with the weight of the bucket and the long line, it puts us right around 6,000 pounds, 5,800 pounds.
So an interesting tidbit there too is you can carry 6,000 pounds, but the helicopter weighs 5,100 pounds.
Yeah, the empty weight is 5,100 pounds.
So it can carry more than its own weight.
Yep.
That's pretty impressive.
Yep.
So sorry, back to this.
Back to the bucket. Yep. Some of the unique features with this specific model, it's variable drop. So in the cockpit, we can hit the button, open the valve, and we can control, if we want to split the drop. If we want 300 gallons here and another 300 gallons here, if we want to just crack the door and mist a long strip of water, we can. So it's very useful for the firefighters.
How do you know the flow rate? Are you just from experience?
Just by visual.
Oh, okay.
Yep. And I can watch my weight gauge. So if I know I want to split the load, if it's 5,000 pounds, I'll just release until I'm at 2,500 pounds, and then I know I've got half the water left.
Does the helicopter lift?
It will.
Are you compensating?
Yep, it's kind of a natural effect. We'll lower the collective as we do that. But yeah, if you didn't do anything and you kept that high power and you release that water, you'd shoot up like a rocket.
Okay.
Yep.
And then it sucks as well. It doesn't just... So there's 2 ways you were telling me about getting the water into it.
That's correct. Yep. So we can... the best way, the quickest way would be to come into a big reservoir pond, and the weight of the bucket sinks it underwater, and we just pull it up and it opens up the bucket and we fill the bucket and out we go. But if we're in the mountains, which a lot of these places in the Sierras are, there's not a lot of big reservoirs. All we need is about 18 inches of water, and these 2 pumps in here will fill the 660 gallons in 40 seconds. Very quick.
So you don't open the valve, you just pump?
Don't open the valve, hit the pump, it sucks it up from underneath. And fills it up. And
then you go by that on weight. You just go full and fly.
The bucket's usually sitting on the creek bed at that point. So it's a visual. I just watch it sort of fill up, and then once it's overflowing, I know I'm full.
Okay.
Yep.
And how long is this cable? How far below you is the bucket?
So the cable assembly from the end of the long line to the bottom of the bucket's about 20 feet, maybe 18 feet. And then the long line to the aircraft is 150 feet. So we're, close to 175 feet.
Okay.
Yep.
So it's kind of down there.
It's down there.
Small.
Yep. But it's nice. That extra length is really helpful in the big timber. If we're going into a creek to try to get water, we get that extra space above the treetops, and then it keeps us a little bit higher from the ground, so the rotor wash isn't interfering with the firefighters.
Oh, exactly. Yeah.
Yep.
Because that'll put out a hell of a lot of rotor wash, and you don't want to be fanning the flames.
That's correct.
Yeah.
The K-Max, compared to everything else, is extremely low rotor wash, but nonetheless, if you take an aircraft that's trying to support lift for 12,000 pounds, that'd be the weight of the bucket and the weight of the aircraft, it's going to put some rotor wash down.
Right.
And if the wind is just right, it'll blast the ground as well.
Yeah. Excellent. So here we are in the cockpit, which is single seat. Kevin, show us some of the big, more sort of obvious controls, what they do.
Yep, you bet. So the dash is laid out very efficiently. Everything on the left is your engine health. So we've got for us, our main limiting factor for the most part is our weight gauge. So we've got weight, RPM, torque. We've got our fuel. We've got our NG, which is how fast our compressor's spinning. We've got the temperature of the engine. All that health gauges is on the left. And then the majority of our navigation, altitude, airspeed, trim, all that is on the right side. So our main GPS is in the middle, our main radio comm, and all of our switches here. And then up above, which you probably can't see, is all of our radio package. So it's laid out very simply. It might look like a lot, but it's an extremely simple cockpit. Controls on the cyclic. We can release the cargo hook electrically, so there's a button there to do that. We can control the bucket from the cyclic. We can control the radios from the cyclic. And then our collective, which is our up and down lever, this is our primary function for the bucket. So we can do bucket release, which is drop in the water. We can do the pumps. We can pump water into the bucket on there. This aircraft has a siren, like a loud hailer, so we can hit that siren, which we end up using a lot.
Or for like, get out of the swimming pool, I need some water.
Yeah, or a lot of people are very interested in the K-Max, so we'll land at an airport and people want to walk up to it instantly. And with the K-Max, you can't approach from the sides.
Yeah, because the blades are lower.
Yeah, so people want to run up and they want to come right up the side and see the pilot, because usually the door's off. So a lot of times we hit that siren just to stop people from approaching the aircraft. But then in the air, if we're doing work on a fire, I'll use it to get firefighters' attention. If we're doing construction work and I see a hazard, like maybe I'm coming in for a set and I see the rotor wash starting to blow things away, I'll hit that siren and I'll point to a hazard for the guys.
Oh, okay.
So it's really helpful. And then emergency functions, so we can emergency control the fuel control from the collective as well. So very, very simple.
So the gear, for me, as a first-time K-Max viewer, I'm seeing very small tires. I mean, that looks like it'd be on a Cherokee Warrior. Mooney discs. Everybody knows I like Moonies. Rubber Mooney discs. And then the nose wheel looks like it's off a 182. For such a big, heavy, capable helicopter, tell us about the gear and why it doesn't have skids.
Sure. So most heavy lift aircraft are going to be on wheels, and the main reason for that is the amount of rotor wash they put down. They need to be able to taxi into their landing areas. If we came in and landed, right next to airplanes, general aviation aircraft, we'd be blowing dust and crap all over the place. So the wheels are a taxi function, so that we can be kind neighbors.
Yeah.
These wheels are small.
Airports.
Yeah. The wheels are small. The aircraft's not designed to come in and land at speed, so we're really not concerned with the wheel needing to take that force that you might have like on a big jet or something like that. These struts that you see it sitting on are actually what take out the force when we land. So this is an oleo strut.
And that's just shock absorber.
This is the shock absorber once the strut is compressed. So when we take off, you'll see this strut drop out a good 2 feet.
Oh, okay.
So they're basically like big shock absorbers that we come in and land on. That takes the majority of the force when we set down. And then the aircraft, this little strut right here, this blanket on the term for it, but
shock absorber
will absorb the force once the strut's compressed.
Oh, okay. So it sits on the bottom of its travel.
Yep, exactly.
Resting on the rubber.
Yep.
Okay. And then to taxi it, it's just like any helicopter. You've just got enough forward thrust to roll, but not lift.
Exactly. So we'll take the brakes off. We will add some forward thrust, and then you can steer two ways. You can steer with the pedals and add yaw, which will spin the aircraft or yaw the aircraft. Or you can do braking, which it would be similar to an airplane. You just tap the left brake and it wants to spin to the left.
Okay. And then obviously the big old beam of gear is simply because it's such a narrow helicopter.
Exactly. If the gear were right here, it would really want to tip over.
Oh, yeah.
So this landing gear boom is to help that tipping tendency on the ground. Which
is there anything in that? It's not used as a tank for fuel or anything?
Nope.
It's just a hollow pipe.
Just a hollow pipe.
Okay.
Yep. Yeah, the K-Max has a very strong tendency to want to get into dynamic rollover, just because of the nature of that design. So the length of that boom is essential. If you went any smaller, it'd be even more tendency to roll over.
And then the other day I saw you coming in sideways.
Yep.
A long way coming in sideways. Is that just so you can see the bucket?
That's part of it. Yeah, we fly sideways a lot. The K-Max is a big wind sail. It likes to be into the wind.
Oh.
It's very happy into the wind. So if we're slow and we try to take a crosswind, you can think of the two rotors as like two dragon heads. If you feed the dragons not equally, she gets upset and she's bucking and kicking.
Okay.
So if you let the nose into the wind, she'll fly sideways really nice.
Oh, okay.
Yep.
Yeah, no, that looked great. Everybody on the airport who saw it coming in is like, wow, that thing is totally sideways to the wind. So let's go to the back where there isn't a tail rotor and see what's back there.
Yep.
So here we are, the back end of it. Look how narrow that thing is. And then one engine, You can see the blades and the masts at the different angles and how they interlock. So Kevin, tell us a little bit about the rudder and whatever that is.
Yep. So the tail, from essentially the engine back, all this stuff is just to make it fly like a helicopter. It just needed these fins and these streamlining features to make it fly through the air.
Oh, so it would just track.
Yep, exactly. So it track through the air. So some of the unique features starting, I guess, forward back is we have these two vertical stabilizers. These do a couple of things. They move with the collective. So as the pilot increases collective or lowers collective, the whole stabilizer moves.
Oh. Sorry, I just had to get a bit of gratuitous footage of a Skywagon taking off. Sorry, Kevin.
All good. So the aircraft creates so much lift. In forward flight, it wants to endo, so it wants to nose over. So that little stabilizer moves, and as the pilot adds power, the stabilizer moves and essentially creates negative lift to help keep the tail down.
So that's automatic relative to your positioning?
Yep, that's a cable linkage. We don't control it. We just move the collective and it moves.
Okay.
So when we're in a hover, no forward airspeed, you'll see that moving, but it's not doing anything for us aerodynamically. Once we get into forward flight, it helps keep that tail down and stable.
Okay, like that single one on a Black Hawk or a Huey?
Yeah, very similar to that.
So if you move that manually, would something move up on the rotor masts?
Nope, it has nothing to do with the rotor system.
Okay.
Yep, completely independent.
Wow.
Yeah, we can move it a little bit here so you can see how it moves. It doesn't have too much input, but...
Oh, that's a lot of range.
Yep.
Wow.
Moving down the tail, so some of the other unique features, we've got another big vertical stabilizer. Again, that just helps it fly straight through the air. The tail is actually similar to an airplane, so we have a rudder. So when we're in a hover and we want to yaw, we talked about the differential lift in the rotors, and that differential lift is what causes us to yaw. When we're in forward flight, that system's not quite as effective. So in addition, when we push pedal, this rudder moves exactly like an airplane.
So will that flap around in hover but do nothing the same?
Exactly.
Okay.
So it's moving in a hover just like the stabilizer there, does nothing in a hover. Once we get into forward flight, this acts just like an airplane rudder and helps drive that tail around.
And this?
This is a feature that Command added. There's a little strut, a little gas strut in here. So the only purpose of this is to protect the structure of the tail. The tail bolts on with 5 bolts right here, 2 on this side, 1 on the bottom, 2 on the other side. So to protect this structure, if the aircraft were to come in and slam the tail into the ground, this strut protects it, and you basically have this much motion before the tail would be scrapped.
Oh, really?
So all you'd have to do is replace this.
And that doesn't move?
Nope.
Oh,
Yeah.
Just, okay. Wow.
Yeah.
It's a completely different machine that flies apparently in a very similar way to a helicopter.
Yeah, very similar.
Yeah.
And that gas strut's one way. So once you've hit it once, it stops. You can't pull it back out. So once you've gone all the way, you have to pull that off. You would do an inspection on the tail, and then you would replace that strut.
So when you come in from a job and it's up here, all your buddies can see what happened.
Exactly.
Okay. So the main thing about this is obviously there's 2 rotors. We've been over a little bit, but in more detail, just talk about how the input is from each of the blades to how you fly it.
Yeah, it's a unique design. If you look at the blade there, you see this blade that's rigidly bolted to the hub, which is the only one in production, the only one in the world that's like that. Typically you would see a rod there with a bearing, and the entire blade would be pivoting at the hub. So our blade is bolted to the hub. If you go down the blade, you see the flap at the back.
Pilots.
Yeah. So from where the blade's bolted, you go down and you see the flap that's attached to the trailing edge of the blade.
Right.
That's kind of Command's unique design. So to get there, before we talk about the system, let's kind of go back to the cockpit. The pilot's sitting in the cockpit, he makes an input. The input goes into a mixing box. From the mixing box, it goes up through a series of control rods. There's no hydraulic boost in the system at all. It's old school push rods. Goes through the system. The stationary input is transitioned into a rotating input, like any other helicopter. A standard helicopter, they would call that a swash plate. We don't have that.
And that would be up on the under the blade.
Exactly.
Yeah.
It would be up there. For us, it's called an azimuth, and it's down below in the cargo bay there. But it's essentially doing the same thing. We're putting a stationary input into a rotating body. So then that rod, that input, goes up through the center mast, down a hollow pocket in the blade, all the way to this flap. So when we move the controls, cyclic, pedal, collective, all we do is move that little tiny flap. And then that flap acts as a driving force and drives the blade. If it wants the blade to go up, it forces the blade just by moving that flap. It redirects the airflow to bend and go up.
So it's like a mini aileron.
It's like a mini aileron.
And there's no, what's it called when a helicopter blade does that?
There's no pitching up there. Yep, that blade is bolted to that hub.
Just flexing it.
Just flexing, which is why it's made out of wood. Today, this aircraft was designed in '94. The airframes are still off production as of 2018. But even today, with all the technology, it's a handmade blade out of wood. And the reason behind that was, at the time, the wood was the only thing that could withstand that repetitive bending and flexing.
And if you had to replace the blades, how much is a blade?
Oh, you can't do one blade. They have to be two at a time so that they're balanced. Gosh, I believe a blade set's around $1 million.
What?
Something like that.
God. Cut. So obviously a lot of moving parts in this entire system. Kevin, could you go up there and point out some of the detail?
Yeah, let's get some close-up inspection.
It's pretty tall, this thing, isn't it?
It is, yeah. The top of the rotor system is 13.6 feet.
Here we are.
So Mark, you were asking about these white things up here. These are essentially shock absorbers. We call them dampeners. So there's two on each blade. This blade can lead and lag 12 feet.
12 feet?
In flight. And these dampeners help support that movement. Once we're in flight, it's not moving all that much. It's probably moving, a couple feet.
Yeah.
Once we're in flight, it's not taking up that whole 12 feet. That's just the full range of motion it could move. Yeah. But these dampers are helping to keep the forces in
Is that a K-Max thing, that amount of lead lag? Do other helicopters have that much?
That is probably more on the higher end compared to other helicopters. It's a lot. Yep, so these help support the lead and lag, the dampening of that force. The other motion that this blade can do is it can teeter. And right now there's droop stops that help keep that teeter in check. If I remove the droop stop and we let the blade teeter down, you can see now its range of motion comes within 2 feet of the ground. So in flight, that's how far down that blade can come.
So that's why it says only approach from front, because if you came from the side when it was running, the blade is here.
Precisely.
Yeah. And the other thing that I noticed is the reason it's so tall must be to keep the tips off the ground.
That's right. We need that. We need the height of the airframe so that blade has all of its range and motion. Because when we set down, we're going to be within 2 feet of the ground with that blade.
So in normal flying, when you're landing it, it's like that?
It can be there.
Yeah,
it's typically higher. It's typically sitting at around 6-7 feet. But if the pilot was moving the controls a lot, it potentially could come that far down. So the engine, bam. Let's see what's going on here. So at a first glance, if you're a helicopter guru, you'd notice this looks just like a Huey engine or a Bell 205 engine, which it is. So this is a T53 17-A1 motor. The only thing they did different with this versus a Huey engine is they modify the nozzles to get a little bit more torque out of it. So thermally, this puts out 1,800 shaft horsepower. The aircraft only uses 1,050 shaft horsepower to fly. Yep. So all the lifting we do, 6,000 pounds, we're down at about 1,300 shaft horsepower.
Why would it need the excess?
That just gives us a margin.
Oh, okay.
Yep. So as we go up in altitude, it helps support that increase in thermal dynamics as we go up. Because the higher we go, the hotter it gets. So it gives us that leeway.
What's the TBO on this? Is it like a hot section, and what's its lifespan?
Yep, it breaks it apart. So for us, a hot section inspection, essentially it's every 3,000 hours. There's a few more little details in there, but roughly to make it simple. Every 3,000 hours, we're tearing this open and changing different components.
Is that how many hours in a season would you put on an engine?
A typical fire season will be 350, 400 hours, and then construction on the other side is another 500 hours. So we're probably just shy of 1,000 hours a year.
So every 3 years?
Yep. Yep.
Okay. Excellent. So here we are again, just finishing up another video with Kevin. Thanks very much for bringing in this K-Max, and thanks for being so informative. I mean, it really, there's not a lot of people that are as good at explaining things as clearly as you were. So thanks a lot for bringing that in.
Yep. Appreciate your time, Mark.
And if you enjoy the video, there's a little subscribe link here and a bell. Click on the bell, you get notifications. And we do videos like this. There's probably 100 or so on our Skywagon University site. So click through them and have a look and subscribe if you enjoy them. And thanks for watching.